Hello, we want to talk today about waves in three-dimensional space. So far, what we have done is in 1D, the one dimension, there were two kinds of waves. You had a standing waves and you had a traveling waves, right? You might remember standing waves. An example of that was if I had both sides fixed, it was finite. You had one side fixed, but the other side could be free, or both sides free, but it was finite. So basically you have a dimension in which this thing is finite. Then in that finite, when waves can go out there and then they have to bounce back, and so it sets up a pattern here which we call standing waves. An example of that kind of wave was some amplitude A, and then you had a sine or cosine, some k knx, and the corresponding cosine or sine omega nt. You could have a phase constant. So this is an example of a standing wave. So these kns were discretized, kns discrete. Okay. A traveling wave, maybe have a one place where finite, but then at least this dimension is infinite. So if I got the start or somehow started by vibrating here, the wave will just go on forever. So an example of this kind of wave, which we call harmonic wave, and the harmonic wave looked like say A, some amplitude, cosine k times x minus omega t, plus some kind of phase constant that tells me how I started at time 0, but k here is continuous. So it's a real number, and it spans the real line from 0 to infinity. Here on a real line it will go, so it will have only some discrete values. Okay. So that's 1D, and fundamentally we were solving classical wave equation, and that looked like d square size over here is the y coordinate. If you had a longitudinal wave, it will be the some displacement along that, so size some displacement. I'll write it like dx square, and I'm going to go 1 over v square d square psi dt square. Well, what will happen in 3D for this classical wave equation? You can see I'll have x, y, and z, right? So you'll have three such contributions. So, and on this side it will be the same, the time and speed. So it will generalize. I'm not going to derive this, but generalize to mathematically speaking, it's going to look like in Cartesian. So if I have more than one dimension, we can use different types of axes, different coordinate systems, and in Cartesian it will look like d square psi dx square plus d square psi dy square plus d square psi dz square as 1 over v square d square psi dt square. So this is a this is called classical wave equation. Classical wave equation in 3D in Cartesian coordinate form. If you want to write more generally, you would notice that this stuff here in from Calc 3, you would know that you can have a vector operator called del, which is in Cartesian looks like this: I hat d dx plus j hat d dy plus k hat d dz. Of course, this is required something to act on, right? And then there is a del dot del of, if you took a dot product, so I hat with I hat, so this will give you another operator in Cartesian. But these operators can be written in other coordinate systems, like a spherical coordinates, so a spherical or cylindrical, but this is Cartesian form, right? In Cartesian form. So left side here looks like over there. So in generally we write this guy as del square, and we can write this not specifying which coordinate system we're going to do. Del square psi equals 1 over v square psi dt square. So if my geometry, suppose I was working with an oscillator, a wave generator was spherical, and it was generating a spherical waves, okay, then I would want to use this del in a spherical coordinate, and it's going to have, you know, a different type of formula. It wouldn't just look like this. It would use r, theta, and phi. I'm not going to go into that, but just want to want to show you that this generalizes, and you can have any coordinate system that is suitable for your problem. So here is a pond, for instance, and you drop a stone, and you might have seen the ripples go out like that. Well, there you would want not 3-dimension, but you may want do a polar coordinate, right? So you will write this del square in 2-dimension, and it's going to use polar coordinates. Polar coordinates would be r and theta. So the basic idea is same, and we're not going to do it. So we'll go back to this, and we'll say we want to do Cartesian. Well, similarly to 1D, you will have a standing wave, and you're going to have a traveling wave, okay? And so you'll have two types of thing. A standing wave will you'll have definitely you're gonna have depending on, say if I have a box, and my waves are restricted inside the box, then the wave from in this direction has to bounce back and forth. Waves in this direction has to bounce. Waves in top have to go bounce back and forth. So you'll be it's called resonator. So you will get what is called resonator, and you won't have all wavelengths, but just the k's over there are, there will be k n along the x-axis, km along the y-axis, and let's say km and say p along the z-axis. And these numbers will be discrete. N will be like a go through 1, 2, 3. Let me stop here. I'm gonna come back to it in just a moment. Okay, so we're talking about we still see two kinds of waves. We're gonna see standing wave, which will happen in a resonator. It will also happen, say you had a tube like that, and this side went to infinite. Maybe you had something that was source of a wave, and the wave will go like this, but in this dimensions and that dimension, so along top to bottom and front and back, this is a finite. So you say this is the z-axis, this is y-axis, and this direction is x-axis, and this direction is z-axis. Then you'll have a traveling wave in z-axis and a standing wave in x and y. Okay, so this is an example like that, and this is fully closed example like that. Or you already seen standing wave in one dimension. So this is standing wave in 3 dimension, this standing wave 2 dimension, and we had example of 1 dimension. So I'm not going to pursue this right now. I just want to introduce you to these ideas. Then we can have a traveling wave, which means for instance, here is a sun, and it kind of emits light, and it's just going everywhere. We assume it's going spherically. So this is in free space. It's go all the way to infinity. So this is akin to when you had one-dimensional and wave could only go on this direction, right? And this went to infinity. And this one is going infinity in all 3 directions, right? So this is a 3-dimensional analog of this guy, which we had in 1 dimension. So this guy was emanating and the wave was going in just 1 dimension. So this is an example of 3-dimensional wave. Okay, so if we wanted to do a 3-dimensional wave, and let's look at just traveling wave first, and we're going to do standing wave because this requires a little more boundary condition matching and things like that. We're going to talk about in another lecture, but the traveling wave in 3 dimensions. So this will be restricted to traveling wave in free space. We should say free space. It's just in vacuum or just 3D space. 3D space. Okay, so just look at 3D space. By free space, I would mean just there's nothing to reflect on, or it's just propagating. Also called propagating waves. All right, it's going to we will look at what is called plane waves. So this is an example of a spherical wave. and we want to look at a plane wave, and we'll see why it's called plane. Okay, basically, if I had a wave front, it will look like a plane, you know, in all, so infinite in both direction. The wave will, this wave, whatever the wave is, it's, the wave is going in particular direction, and that's normal direction, normal to the front. So we'll see mathematically why this, how this is a plane wave. Okay, but first I'm going to write down the answer. So we have a psi of x, y, z, and t, and I want to write a plane wave. So it's going to have, if I'm in this plane, at any point in this plane, that's x, y, z. This point on this plane is x, y, z, and at that plane I need to say how much amplitude is displaced, whatever the quantity is. For instance, if you're in an electromagnetic wave, this will be, say, electric field, how much electric field is different at this point from 0, right? If our sound wave, I would say how much pressure is different from ambient pressure at this point. So the property will differ, but all those property we're saying has some value psi, and it just representing displacement from equilibrium, right? So that's what this is representing, and displacement of what property? That property varies from types of waves you're looking at. Okay, this is going to have some kind of amplitude. Okay, and if this was a vector wave like electric field, this will be a vector. Then we'll have a, say, cosine. Now it's going to be all function of x, y, z. So we had a k times x for one dimension. Naturally, you may say, what? I would have a kx times x plus ky times y plus kz times z. Makes sense, right? Minus omega t, and there will be a phase constant, which is unimportant if you just one wave, but you have multiple waves, then their relative phase constants are important. You can set, if you're just one wave, you can choose t. You can absorb this in choice of t. For instance, you can say, hey, this is simply minus omega t prime. So instead of using t, I'm going to use a t prime, and t prime is my original t minus phi over omega, and omega is a particular frequency. So this is angular frequency of the wave. First thing notice is a plane wave. A plane wave is a harmonic wave, so single frequency, and it is a harmonic wave. So harmonic wave, because it is harmonic function of the frequency. It's a pretty straightforward generalization of the harmonic wave on a string, you can see. So omega is frequency, but what are these k's? Well, k, it looks like a k should be a vector, and that can be kx, ky, and kz, and xyz should be this vector, should be x, y, z, and so this thing should be more compactly written as k dot r, right? K dot r. So okay, So I've got this. What K is called wave propagation vector. Of course, the magnitude of K, its magnitude will be square root of kx square plus ky square plus kz square. Well, this magnitude we will denote with a just without the arrow, and this is a wave number. This property called wave number, and you've already met wavelength. Wavelength is related with k. Lambda is 2 pi over k. Okay. If you look at these, what this is representing, so I have some Cartesian coordinates, maybe x, let's call this x, let's call this y, and let's call this z. So if here is a point x, y, z, and I am going to say that my wave is traveling in that direction, z direction. So you would see that k actually is 0, 0, k. It's only the z, kz, and this is ky, and this is kx. And you'll find we'll have psi of x, y, z at that point, comma t, just look like a cosine kz minus omega t plus phi. So you might say, hey, this looks like one-dimensional wave. It's not true. It also has x and y. Just because this thing doesn't depend on x, y does not mean it does not have x and y. What it is if I look at this thing for a constant phase, so say look at kz minus omega t at some time t, okay, plus phi, some constant, which we can just set to 0. You can even set t equal to 0. So if you look at where it looks like at t equals 0, so kz equals to omega t minus phi. So this has some value, say has some value a. So if you look at this, you have a kz equals to a. Well, this is a plane parallel to, this is plane parallel to xy, right? So this thing has same value at all of these planes. Okay, such a thing where this thing is constant, same value. Of course, if I give you a particular value, say I give you 0.1 radian for this, well, multiplied by a, this is given number, so this will be same value for all of this, and this is called wavefront. So as if I look at a particular value of, say z, say z1, for that value this has 0.1 radian at this time, set t equals to 0. So the wavefront, if you look at the wavefront at some other time, some other place, let's say z2, is also parallel. So wave fronts in this space are parallel to each other, and they are planar. And the direction the wave fronts are moving is the direction of this vector k. So this vector k tells me which direction the wave will propagate. You might say, hey, you just did for you set kx and ky 0. That's very nice, well and good. How do I know it's going to be good for other situation also? Well, we can say more general. So suppose let's look at some general. So it's still, this time I don't set anything, okay? I have x, y, and z, and here is a point x, y, z. Maybe this wave is moving that way, okay? So the k vector, I'll just say it's got some kx, some ky, some kz. Okay, this is just moving in a very arbitrary direction. So if I look at phase, which you can say phi at x, y, z, phi at sometime t at this point, that's kxx plus k yy plus k zz, and I'm just gonna forget about say phi equal to 0. We picked time so that this is 0, okay? Just for not writing too many phis everywhere. Now this phi is not the same as that phi. This is the entire thing I'm writing out, okay? And that depends on x, y, z. All right. So when this has some constant, meaning say I'm looking for wavefront, right? Looking for wavefront. So that if you look at this and t is fixed, so if your t is fixed, t fixed. So if you look at this equation, k dot r, so this r vector is okay, r vector k vector is that, and this is the r vector. So k dot r equals to some, let's call it some constant. This thing is omega t is constant. This is what do you think is it? This is the equation of a plane with normal is k direction, right? Normal direction is same as k direction. So what we have is k dot r minus some a equal to 0 with k dot a equal to some c. That c is some constant, okay? So this is equation of a plane, and so the plane is this plane. This guy is 90 degrees to it, and this vector is some r minus a vector. So this some arbitrary point in that plane is a vector. So this is so r minus, here, let's see, if I do r, go here, if I add this vector, so this is a minus r, a minus r. So if I go here r, add this, I get the a vector, right? Okay, so you can see why we even for arbitrary direction k, the wavefronts are plane wavefronts. All right. We're gonna do one more property. Okay, so we want to know how fast the wavefront is moving, right? So how fast wavefront is moving. So if I have a wavefront like this, and so some arbitrary, it's r, and at some time t, the wavefront is here, and it's moving in that direction, right? 90 degrees to the wavefront. Okay, so this is the wavefront, is moving 90 degrees to the wavefront. Okay, so let's see, in a little bit later time, the wavefront will be here, right? In this. So this point we're talking about, go over there. So let's call that dr. And so the wavefront is from here, or if I look at that point is r plus dr, and this wavefront here is t plus dt time. So if I look at phase here is same as phase here. This phase is same. So phase was k times r minus omega t, and this is same as k is constant dot r plus dr minus omega t plus dt. That just means if I k dot r cancelled out, and you have a k dot dr minus omega dt equal to 0. Now this does not mean, okay, this is bad math, okay, the dr dt will be the velocity is equal to omega over k vector. This is stupid, okay. Here what you're getting is I have to go in the direction of k. All right, so in the direction of k. So this is I'm going to interpret this as take the k and k dl. That's if I took a dot product. That's dl is dr dot k hat. K hat is k divided the magnitude of k. All right, so dl, not vector here, dl. So k, so I'm in the direction, so this distance is dl, okay, not dl vector but the dl, this distance is dl, minus omega dt equal to 0. Now dl over dt will be the how much, with what speed my wavefront is moving, and this is omega over k. So you might remember this, but this is, we're doing three-dimensional, and this is called phase velocity. Because guess what, why do you think it's called phase velocity? Why are you confused? See this, what I did, I am looking at constant phase. So I said this is at this, when the wavefront is like this and the wavefront is like that, they're the same phase. So it's a phase at which constant phase points are moving, and so that's the phase velocity. This is not we'll see that just like the group in the one-dimensional case, group velocity moves at another speed, right? So now if you had more than one harmonic wave, so if you had more than one frequency, okay, then harmonic waves, for instance, you had like a two harmonic wave, then you had a beat phenomena, then you can have a group velocity which will be d omega over dk. You may say, well, will that be, this was the case in 1D, this is the case in 1D, right? So what happens to group velocity now? You will not be surprised that it's going to be a velocity, right? So you'll have a dkx omega in the I hat direction plus dky ky omega in the j hat direction, d omega dkz in the k hat direction, and that can be you can see I'm writing this derivative in a weird space. It might remind you that this is some kind of del. If you're in a del using x, y, z, this vector operator was d dx I hat plus d dy j hat plus k hat d dz. So you could say, yeah, well, this is, I could actually really be fancy. I could say del, it's kind of like that, but in the k space. You better do in the k space of omega. So this is a shorthand way of writing group velocity vector. So group velocity will be a vector. Phase velocity is, we already know which direction it's going. So if you want to do velocity, you'll have a omega over k in the k hat direction. That will be the velocity, and you can call this phase speed if you choose to. So phase speed, nobody calls that, everybody calls it phase velocity, but we mean the magnitude, but because we already know the direction. All right, I'm going to stop here and see how I did. I think recorded. Hello, just wanted to complete our discussion on standing waves, standing waves in 3 dimension. Consider a rectangular resonator. So x-axis is this way, y-axis this way, and I use a right-hand coordinate system. That z-axis is that way. Is a box. This is where I place the origin, and you go there, x equal to a, this is y equals to b, and z equals to c. So this says a times b times c dimension box. For instance, this can be an oven, and I heat the oven a particular temperature. Then this what happens inside the oven is you get electromagnetic waves, right? And there you will get a black body radiation there. So inside there, if this was if this is an oven at temperature T T Kelvin, okay, then you will get if you had a little hole here, the light that will come out or EM wave, let's call it EM wave out, this will be a black body radiation. You might have heard of this black body radiation, and this has played very important role in quantum mechanics development, quantum theory, and then eventually quantum theory was explained through quantum mechanics. Okay, so it's kind of has a distribution with frequency, intensity of particular wave. It comes out different frequency, and it has a distribution where that depends on the temperature. All right. I will not say more to that. You will learn that in modern physics. You're gonna learn this part in modern physics if you have not studied that already in introphysics. Okay, so that's one example of the waves that it sets up a standing wave in all three directions. Okay, and a solution is if psi is amplitude of the wave at some point, let's inside a point called xyz. So xyz, and we want how much the amplitude differs from zero. So this is, as you remember, this displacement variable, right? This is displacement of some type. In electromagnetic wave, it can be electric field. If this was some kind of sound, your resonating sound, this will be how much the pressure is different from the ambient pressure. Okay, so those are some of the physical things that can happen. So when I have a resonator, what I'm going to have is some amplitude. The wave will reflect back and forth. So when it's turning, it's going to be zero at the say this phase, and in the back phase, so x equal to 0 is 0 and x equal to a is 0. So it's going to be sine some kx, but can't be some arbitrary kx. Some let's call it nx x. Okay, and if you had a string along the x-axis, so you might know that this will be nx pi over a, right? Nx pi over a. So it's going to when x equal to a is going to be 0, and x equal to 0 is 0, and nx will be it shouldn't be 0, because it's 0 then it's automatically everything is 0. So this will be, you can have plus minus 1, or you can show modes with the plus minus are the same. So it's very much like the string system. So that happened around the x-axis. then very similar thing is going to happen along the y-axis. Why not? K in y, y, and then same situation along the z-axis, but K in y is supposed to be vanished when y is b, so it will be ny pi over b, and this ny will be again 1, 2, 3, etc., right? So then I'm going to get a sine k along the z-axis. K in z, it will be nz pi over c, and nz will be 1, 2, 3, etc. And then I'm going to have cosine omega n t, and I'm going to have a phi of, some kind of phase constant. All right, so what's the omega n gonna be? Well, you can see what the omega n has to be for each one of these modes. So these modes are being labeled with the nx value and ny value and nz value. So I can say I am in a mode nx along the x direction and ny along the y direction and nz along the z direction. So in this mode, what's the frequency? Well, the frequency, this has to obey, right? How do I get frequency? I say it obeys classical wave equation. So I plug this into classical wave equation. Del square psi is 1 over v square d square psi dt square. So this will give me, when I do x derivative, I get that. I get it back. I get k nx square minus, right? Sine goes to cosine and another back to sine, and this is minus k n y square, and this is minus k n z square, and then I get on the other side I get 1 over v square minus omega n square, right? So the minus cancel out, and it's pretty clear that frequency will depend on which mode I am in. Okay, so frequency depends on which mode. So I have v square k n x square plus k n y square plus k n z square, and these take a square root both sides, so this is square root. So let's, as an example, let's look at say I'm in mode 1 here and 1 here and 1 here. So we'll have a mode psi 1 1 1. So that's these will be labeling the modes x, y, z, t. That will be some amplitude for this mode, and then sine is going to be pi x over a sine pi y over b sine pi z over b, and cosine, and you can see square root of of course pi square is common, so this is 1 over a square plus 1 over b square plus 1 over c square, this times t, pi, not pi square, pi comes out, not pi, plus phi. So that's the frequency is this, and the mode is this. So if this will be the lowest frequency. You can see that if I picked any other k another value for this, it will be higher frequency. So psi said I'm in mode 2 here, but 1 here and 1 here. Mode 2, 1, 1. So x, y, z, t. A 2, 1, 1 sine 2 pi x over a sine pi y over b sine pi z. Oh, this is c, this mistake. And the cosine will, of course, pi gonna come out, and now I have a 2 over a, so 4 over a square plus 1 over b square plus 1 over c square plus phi. So this frequency times t outside, this frequency omega 211, and this frequency with a pi in there is omega 111. You can see omega 211 is greater than omega 111, but these are all discrete frequencies, and so it's going to oscillate at different frequencies. You can say a whole bunch of frequencies. You can say, I'm going to ask you a question here and leave it unanswered. Say a equals to 1 meter and b equals to half a meter and c equals to, say, 2 meter. Okay, so I've got this dimension, and suppose okay, so what if I have this dimension? So what will be, I missed out the v somewhere, right? Here's the v. So did I put v anywhere? There's a v here. There's v here, and there's a v here. Okay, so there's a v here, and let's say v is equal to let's pick a nice number, 5 meter per second. Okay, find 4, if there's possible, up to 4 lowest frequencies. Okay, so I'm just going to leave this as a something you should work out to get a sense of how the waves pack and what kind of modes you might get in this problem. Okay, so I think this completes our introduction to three-dimensional waves. There's more in the book, and next I'm going to talk about electromagnetic